Welcome to Part 1 of the Keras course, Getting Started with Deep Learning. In Chapter 1, you'll set up Keras, learn its structure of models, layers, and tensors, and build your first neural network on the M-NIST digits dataset. In Chapter 2, you'll explore Keras core concepts, sequential and functional APIs, common layers, activation functions, and how to compile, train, and evaluate your models. In Chapter 3, you'll learn to work with real data, loading datasets, preprocessing, normalization, and splitting data properly. In Chapter 4, you'll build real architectures, feed-forward, convolutional, and recurrent neural networks, and master transfer learning with fine-tuning and freezing layers. By the end, you'll be ready to build and train neural networks for real-world projects. Chapter 1. Getting Started with Keras. What is Keras and why use TensorFlow? Keras. Keras is a high-level interface for building neural networks. It focuses on clarity and fast experimentation. You write fewer lines of code and get readable models. Keras runs on top of a low-level engine called TensorFlow. When you use Keras inside TensorFlow, we call it TF.Keras. TF.Keras connects the simple Keras API to TensorFlow features. That gives you easy model building and access to production tools. With TF.Keras, you can use GPUs and TPUs for faster training. You also get tools for monitoring, saving, and deploying models. Finally, a big community means many examples and pre-trained models. In short, Keras makes deep learning practical for engineers. Installing TensorFlow and Keras. To install Keras with GPU support in VS Code on Windows, just open CMD. Go to your project folder and create a virtual environment with Python-mvenv. Activate it using tfenv scripts activate. Next, upgrade pip using python-mpip install --upgrade pip. And install TensorFlow, which already includes Keras, using pip. For example, 2.16.1 version works best with modern NVIDIA drivers and supports GPU out of the box. You should also add CUDA path to the environment variables on your Windows machine. Before installation, you should check version compatibilities between Python, CUDNN, CUDA, and TensorFlow versions, and also your GPU driver version. You need to consider that newer CUDA versions may not support some old GPUs, so you need to make sure about that. You can find relevant information in this link. Once done, open your project in VS Code. Make sure the Python interpreter is set to your tfenv and run this small test. Understanding the structure. Models, layers, tensors. A model is the main structure that holds everything together. It defines how the data moves through the network from start to finish. Layers are the building blocks of the model. Each layer performs a small operation. For example, it may combine inputs, apply weights, or use an activation function. When you stack layers together, they form the full neural network. Tensors are the data containers that flow through the network. You can think of them as multidimensional arrays that hold numbers. For example, an image or a batch of values. Every operation in Keras works with tensors. In simple terms, data enters the model as tensors, goes through a series of layers that transform it, and finally exits as predictions or output tensors. So remember the chain: models connect layers, and layers process tensors. In this example, first we import Keras and TensorFlow. Then we create a tensor called input_data. This is a random tensor shaped 1, 28, 28, just like a single grayscale image. Next, we create a sequential model. Inside it, we add 3 layers. The first layer is flatten, which converts a 2-dimensional image into a 1-dimensional vector. This makes it ready for the dense layers. The second layer is dense with 64 neurons and the ReLU activation function. It learns meaningful patterns from the data. The final layer is another dense layer with 10 neurons and the softmax activation. This gives us 10 output probabilities, one for each class. Finally, we send the input tensor through the model and print the input and output shapes. The output shape of 1 by 10 means one sample with 10 predicted values, exactly what we expect for classifying digits from 0 to 9. Using Google Colab, Jupyter, VS Code, Keras is flexible and runs in many different environments. You can use it in Google Colab, in Jupyter Notebook, or inside Visual Studio Code. Google Colab is a cloud service from Google. It already has TensorFlow and Keras installed, and it provides free access to GPUs and TPUs. You only need a browser and a Google account. It's perfect for beginners and for quick experiments. Jupyter Notebook runs locally on your computer. It's interactive and lets you run code step by step, see graphs, and edit markdown text in one place. It's a great choice if you prefer working offline. Visual Studio Code, also known as VS Code, is an integrated development environment. It's best for larger projects and for debugging deep learning applications. You can install extensions for Python and Jupyter to get a smooth workflow. No matter which environment you choose, your Keras code will run exactly the same. In this small project, we will train a small neural network on the M-NIST digit dataset. M-NIST has 28 by 28 grayscale images of digits 0 to 9. We load the data from Keras, normalize pixel values, and build a short model. The model flattens the image, then uses a dense hidden layer and a final softmax output layer. We compile with Atom Optimizer and sparse categorical cross-entropy loss. Then we train for a few epochs and evaluate accuracy on the test set. This example is minimal, practical, and runs in any environment such as Colab, Jupyter, or VS Code. Chapter 2: Keras Core Concepts. The Sequential API versus the Functional API. Keras provides two main ways to build deep learning models: the Sequential API and the Functional API. The Sequential API is the simplest. You stack layers one after another, from input to output. It's great for linear models, where each layer feeds directly into the next. Most beginners and small projects start with sequential models. The Functional API is more flexible. It allows you to build complex models with branching paths, multiple inputs, or multiple outputs. You define the flow of data manually, connecting layers like a graph. Functional models are used in research, advanced architectures, or when combining models together. Both APIs share the same layers, optimizers, and training methods. You can switch between them easily once you understand both. We start by importing Keras and layers. Next, we create a sequential model. The first layer defines the input shape, 28 by 28. Then we flatten the image, followed by a dense layer with 128 neurons and ReLU activation. The final layer has 10 neurons and softmax activation for 10-digit classes. Finally, Model Summary prints a short report of all layers and parameters. This is the simplest way to build a network. Here we use the Functional API. We first create an input object with shape 28 by 28. Then we pass that input through a flatten layer. The output of that goes into a dense layer with 128 neurons and ReLU activation. Finally, we connect that to a dense output layer with 10 neurons and softmax activation. We define a model by specifying inputs and outputs to Keras.model. This method allows more control and is used when you need custom data flows, shared layers, or multiple outputs. Common layers. Let's look at the most common layers you will use in Keras. The dense layer is the main building block of neural networks. It connects every neuron in one layer to every neuron in the next. You specify how many neurons it has and which activation function it uses. The flatten layer reshapes multidimensional data into a single vector. For example, it turns a 28 by 28 image into a one-dimensional array. This allows the dense layers to process the image data. Dropout is a regularization layer. It randomly deactivates a fraction of neurons during training. This helps the model generalize better and prevents overfitting. Batch normalization normalizes data between layers. It keeps activation stable and allows faster and more reliable training. COM2D, or Convolution 2D, is the core layer for image processing. It scans the image with small filters to extract local features like edges and textures. Commonly, you follow Con2D with max pooling to reduce spatial size. A typical pattern is COM2D, then batch normalization, then dropout. This pattern helps learning, stabilizes activation distributions, and prevents overfitting. Transformers use attention to model relationships in sequences. A transformer encoder block has multi-head attention, followed by a feed-forward network and layer normalization. Transformers are strong for text, time series, and advanced vision models. Use COM2D for standard image tasks and transformers when you need global context or sequence modeling. You can combine these layers freely to build efficient deep learning models. All of them are part of Keras.layers. In this example, first we import Keras and layers. We create a sequential model for small color images shaped 32 by 32 by 3. We add a convex 2D layer with 32 filters, kernel size 3, and ReLU activation. Then we apply batch normalization to stabilize activations. Next, we reduce spatial size with max pooled 2D and pool size 2. We add a second convex 2D with 64 filters, again followed by batch normalization. Global average pooling converts the feature map to a single vector per sample. We add dropout with rate 0.3 to reduce overfitting. Finally, a dense output layer with 10 neurons and softmax gives class probabilities. Model summary prints the layer shapes and parameter counts. Activation functions. Activation functions control how signals pass between neurons. They make neural networks nonlinear, allowing them to learn complex patterns. Let's compare the most common ones. ReLU, short for rectified linear unit, outputs 0 for negative values and the input itself for positive values. It is very fast and works best in hidden layers. Its only drawback is that neurons can sometimes stop learning when inputs are always negative. This is called the dying ReLU problem. Sigmoid maps input values into the range between 0 and 1. It was used a lot in older networks and is still used for binary classification outputs. However, it can saturate at very high or very low input values, slowing down learning. Softmax is mainly used in the output layer for multi-class classification. It converts raw scores or logits into probabilities that sum to 1. Each neuron represents the probability of one class. Tan H, or hyperbolic tangent, is similar to sigmoid but centered around 0. It is still used in recurrent networks, like LSTM, but less common in modern feed-forward networks. Leaky ReLU is an improved version of ReLU that allows a small slope for negative values, preventing dead neurons. Finally, Swish and GelU are newer smooth activations used in deep and transformer models. They improve gradient flow and are often used in state-of-the-art architectures. Optimizers. Optimizers control how a neural network learns. They adjust model weights to minimize loss during training. Let's compare the most popular ones. SGD, or stochastic gradient descent, is the simplest optimizer. It updates weights step by step using the gradient of the loss. It's stable, but can be slow for large problems. Adding momentum to SGD gives smoother and faster learning by remembering previous gradients. RMS prop adapts the learning rate separately for each parameter. It's great for recurrent neural networks and problems where gradients change over time. Atom is the most widely used optimizer today. It combines momentum and RMS prop and usually works well with default settings. It's fast, reliable, and ideal for most Keras projects. Atom W adds weight decay regularization to Atom. It is especially effective in vision models and transformer architectures. Adagrad gives larger updates to rare features, making it popular for natural language processing and sparse data. Natum or Nesterov Atom adds Nesterov momentum to Atom for even faster convergence, but can be a bit unstable. For most cases, Atom or Atom W should be your first choice. Loss functions. Loss functions tell our neural networks how wrong they are. They measure the difference between predicted values and the actual target values. The optimizer then uses this feedback to adjust the model's weights. Let's look at the most common ones. For regression problems, we use mean squared error, or MSE. It squares the difference between predicted and true values, so large mistakes count more. If your data has outliers, MSE can be sensitive to them. Mean absolute error, or MAE, simply measures the average distance between predicted and true values. It's more stable when outliers exist, but it can converge a bit slower. For classification problems, we often use cross-entropy-based losses. Binary cross-entropy is used when there are two classes, for example, spam or not spam. It expects a sigmoid activation in the output layer. Categorical cross-entropy is used when you have more than two classes, like classifying digits or animals. It works with one-hot encoded labels and a softmax activation in the output layer. If your labels are integers instead of one-hot vectors, use sparse categorical cross-entropy. It does the same job, but uses less memory. Uberloss combines the best of MSE and MAE. It behaves like MSE near zero error, and like MAE when the error is large. This makes it useful for regression tasks with occasional outliers. KL divergence, or Kullback-Leibler divergence, is used in probabilistic models, like variational autoencoders, to compare probability distributions. Finally, hinge loss is used for models that predict margins, like support vector machines. It's not common in deep learning, but still available in Keras. The right loss function depends entirely on your task: regression, classification, or probabilistic modeling. Getting it right is critical for model performance. Sometimes, the built-in loss functions are not enough. In Keras, you can easily create a custom loss function using simple Python code. You just define a function that takes true labels and predicted values, then returns a loss value. This is very useful for special business rules. For example, when certain prediction errors should cost more than others. Metrics. Metrics show how well your model performs, but they don't change how it learns. They're like performance reports during and after training. For classification tasks, the most common metric is accuracy, which measures how many predictions are correct. However, accuracy can be misleading when classes are imbalanced. That's where precision and recall come in. Precision tells us how many of the predicted positives were actually correct. Recall tells us how many of the actual positives we successfully found. If you care about both, use the F1 score, which balances precision and recall. The AUC, or area under the curve, measures how well the model ranks positive samples higher than negative ones. It's especially good for imbalanced data. For regression tasks, we use metrics like mean absolute error, mean squared error, and root mean squared error. MAE gives the average distance between predicted and true values. MSE squares the difference, so it punishes large errors more strongly. RMSE is the square root of MSE, giving results in the same units as the target. Mean absolute percentage error measures average percentage difference and is often used in forecasting or financial models. For image models with many classes, top K accuracy checks if the correct label appears within the top few predictions. Useful when multiple answers might make sense. Choosing the right metric depends on your goal. Accuracy isn't always the best. Sometimes precision, recall, or F1 score gives a much clearer picture. Training, evaluating, and predicting. In Keras, there are three main methods you'll use in almost every project: fit, evaluate, and predict. They form the complete life cycle of your model. Fit is the training step. It feeds your input data and labels into the model for a set number of epochs. Each epoch means one complete pass through the dataset. During this process, the model's weights are updated to minimize the loss function using the selected optimizer. The method returns a training history that contains loss and metric values, so you can plot or monitor progress later. After training, you use evaluate to measure how well your model performs on new or unseen data. This is typically done with the test set. Evaluate runs through the data once without changing the model's weights and reports the final loss and accuracy or other metrics. Finally, you use predict to generate results from new inputs. It outputs values such as probabilities for each class in a classification task or continuous predictions for regression. This is the step where your model becomes useful in the real world, classifying images, predicting prices, or analyzing texts. In summary, fit teaches the model, evaluate tests the model, and predict uses the model. Together, they make up the full workflow of deep learning with Keras. Let's review everything we've learned in this chapter with one complete example. We start by importing Keras, layers, optimizers, losses, and metrics, the main building blocks of every project. Then we load the M-NIST dataset of handwritten digits. Each image is 28 by 28 pixels, so we reshape and normalize them to values between 0 and 1 for better training. Next, we build a sequential model. It begins with a dense layer of 128 neurons using the ReLU activation function. Then, a dropout layer randomly turns off 30% of neurons to prevent overfitting. Finally, the output layer uses the softmax activation to predict one of 10 possible digit classes. We compile the model using the atom optimizer, the sparse categorical cross-entropy loss, and accuracy as our metric. This defines how the model learns and how it would be evaluated. Then we call fit, which trains the model for 5 epochs using mini batches of 64 images. We also include a validation split to monitor performance on unseen data during training. After training, we call evaluate to test the model on the test dataset. This reports the final loss and accuracy, a measure of how well our model generalizes. Finally, we use predict on the first few test samples. The model outputs probabilities for each digit, and we select the most likely class using the argmax function. We then compare the predicted and true labels. If everything goes well, accuracy should be around 96% or higher. Chapter 3. Working with real data. Loading data with TensorFlow.Keras.datasets. Keras makes it very easy to start experimenting with real data. It includes several well-known public datasets that you can load instantly, no extra downloads or setup needed. You can access them through Keras.datasets. Each dataset is already split into a training set and a test set, so you can begin modeling right away. Some of the most common datasets are M-NIST, which contains 70,000 handwritten digit images, great for learning image classification. CFAR-10, which has 60,000 small color images across 10 categories, perfect for practicing convolutional neural networks. And IMDb, which includes movie reviews labeled as positive or negative, ideal for learning text classification and sentiment analysis. These datasets are small enough to train quickly, but realistic enough to teach core deep learning workflows. That's why they're used in most Keras tutorials and beginner projects. Each one comes with convenient preprocessing options, like normalizing pixel values or converting words to sequences, making them ready to feed directly into your models. In this code, first we load the M-NIST dataset. It contains black and white images of digits, each 28 by 28 pixels. The load function returns training and test sets automatically. Next, we load Cipher 10. This dataset includes small color images, for example, airplanes, cats, and cars. The data is shaped into 32 by 32 pixel images with 3 color channels. Finally, we load the IMDb dataset. Instead of images, this one contains sequences of word indices representing movie reviews, along with binary sentiment labels. By setting num words equal to 10,000, we limit the vocabulary to the most frequent words. These built-in datasets are great for practicing. You can test model structures, learn to preprocess data, and benchmark your models quickly without hunting for raw data files. Loading CSV or Excel datasets with Pandas and TensorFlow. In real-world projects, most data doesn't come neatly packaged like M-NIST or CFAR 10. Instead, you'll often get your data in CSV or Excel files. For example, exports from a business system or a data warehouse. To handle this, we use Pandas, a powerful Python library for data manipulation. Pandas can easily read files using functions like read.csv or read.excel. Once loaded, the data is stored in a data frame, which lets you inspect, clean, and preprocess columns. After cleaning, you'll typically separate the data into features, the input variables, and labels, which are the target outputs you want your model to predict. Finally, you can convert these data frames into NumPy arrays or TensorFlow tensors and feed them directly into your Keras models. This approach is especially useful for tabular data, financial datasets, or time series, where deep learning models like feed-forward or recurrent networks can perform well. We begin by importing Pandas, TensorFlow, and Keras. First, we load data from a CSV file and an Excel file using Pandas read.csv and read.excel. Both return data frames, which we can easily inspect or print. Next, we separate our data into features and labels. In this example, the column named Target is our label, and all other columns are used as input features. We then convert these NumPy arrays into TensorFlow tensors using convert_to_tensor to make them compatible with Keras. Finally, we define a simple sequential model for binary classification. It has one hidden layer with ReLU activation and an output layer with sigmoid activation. We compile it with the atom optimizer and binary cross-entropy loss, which are ideal for binary classification tasks. At this point, the model is fully ready to train on your own CSV or Excel data. This workflow mirrors what you'll do in real data science or machine learning jobs. Read, clean, convert, and train. Image data pipelines using Image Data Generator and tf.data. When working with images, efficient data loading is critical. Raw image files are large and can slow down your training dramatically if not handled properly. Keras provides two main tools for image pipelines: Image Data Generator and TensorFlow.data. Image Data Generator helps you load and transform images in real time. It can automatically rescale pixel values, rotate or flip images, and create random variations to help your model generalize better. This is called data augmentation. On the other hand, TensorFlow.data gives you a high-performance and flexible way to build custom pipelines. It's ideal for large datasets or when you need more control, like caching, shuffling, and decimal fast, or parallel loading. Both approaches follow the same general steps. First, resize and rescale the images. Then, apply augmentations, batch the data, and feed it into your Keras model. Mastering data pipelines is a key professional skill. It helps you train faster and build more reliable computer vision systems. Here, we import Image Data Generator from Keras. This tool allows us to load, rescale, and augment images directly from folders. We create a generator that rescales all pixel values to between 0 and 1. It also adds small random transformations, such as rotation, zoom, and flipping. These variations make the model learn more general features, preventing overfitting. Next, we use flow_from_directory to load training and validation data. It automatically reads images, groups them into batches, and applies augmentations on the fly. Finally, we print the batch shape and label shape to confirm that everything works correctly. At this point, the pipeline is ready to feed into a model. This code shows how to use the TensorFlow data API for larger image datasets. We start with tensorflow.keras.utils.image_dataset_from_directory. It automatically scans the folder, loads images, resizes them, and creates a dataset of image and label pairs. Next, we normalize all images by dividing pixel values by 255 using the map function. Then, we call prefetch with auto-tune, which allows TensorFlow to prepare the next batch while the current one is being processed. This dramatically improves input pipeline speed and GPU utilization. Finally, we loop through one batch using take one and print the shapes to confirm everything is set up correctly. This method is ideal for large or complex datasets, and it integrates smoothly with advanced preprocessing or distributed training setups. Normalization and preprocessing. Before we feed any data into a model, we need to normalize and preprocess it. Normalization keeps numerical values within a consistent range, usually from 0 to 1. This helps neural networks train faster and avoids instability during learning. Preprocessing prepares the data in the right format and shape. In image tasks, that means resizing, rescaling, and applying random augmentations such as flipping or rotating. In Keras, you can do this using simple tools like the rescaling layer, image data generator, or preprocessing pipelines built with TensorFlow.data. The goal is always the same. Make sure your model receives clean, consistent, and well-structured input so it can focus on learning meaningful patterns instead of raw noise. Here, we load an image dataset using tensorflow.keras.utils.image_dataset_from_directory. Then, we apply normalization using the map function, dividing all pixel values by 255. This ensures that all images have the same scale, regardless of brightness or color intensity. Finally, we print one batch shape to confirm everything is properly processed and ready for training. Keras provides ready-to-use pre-processing layers that can be included directly in your model or used as a data pipeline. In this example, we create a sequential model that handles all image pre-processing steps. The rescaling layer normalizes pixel values. Random flip, random rotation, and random zoom add variation to the images to improve generalization. These layers work both on CPU and GPU, making pre-processing efficient and easy to integrate into your training process. The final print shows that the processed image keeps the same dimensions as the input, which is important when feeding data into a neural network. This example combines both normalization and preprocessing into a single efficient pipeline. We first load and normalize the dataset by dividing pixel values by 255. Then we build a preprocessing sequence with random flip, random rotation, and random contrast layers. These transformations simulate real-world variations in your training data, helping the model generalize better to unseen images. Finally, we apply the pre-processing pipeline to every batch using the map function. This setup ensures that normalization and augmentation happen dynamically, directly on the GPU during training. It's clean, fast, and production-ready, exactly how image pre-processing is done in professional deep learning projects. Splitting data, train, test, validation. When building any machine learning model, splitting your data correctly is one of the most important steps. The training set is what the model actually learns from. The validation set is used to tune hyperparameters and check performance during training. And the test set is reserved strictly for the final evaluation. It tells you how well the model will perform on unseen data. Typical splits are 70, 15, 15, or sometimes 80, 10, 10. You can create splits manually, or by using helper tools such as scikit-learn or TensorFlow dataset utilities. Always make sure your data is shuffled before splitting. If it's not shuffled, the model might see patterns from ordering instead of actual features. Splitting tabular data with scikit-learn. Here, we import the train test split function from scikit-learn. We first load a dataset from a CSV file and separate it into features and target labels. Then, we split the data twice, once to separate training from the rest, and then again to divide the temporary part into validation and test sets. This gives us three groups: 70% for training, 15% for validation, and 15% for testing. We also use shuffle equals true to randomize the samples before splitting, which is always recommended. Splitting image data automatically. In this example, we use image data generator from Keras to handle image splitting automatically. We create a generator and set the validation split parameter to 0.2. Then, when we load images from a directory, we specify whether we want the training or validation subset. This method saves time and keeps your data pipeline clean. It's ideal for image classification tasks where the data is organized by class folders. Splitting TensorFlow datasets. When you load datasets using TensorFlow utilities, you can split them directly in memory. Here, we first load an image dataset and calculate the total number of batches. Then, we compute the split sizes: 70% for training, 15% for validation, and 15% for testing. We use the take and skip methods to slice the dataset into separate parts. This is efficient and works well with tf.data pipelines. Finally, we print the number of batches in each split to confirm everything is correctly divided. So as in quick wrap-up, using scikit-learn's train test split is the simplest and most flexible option, perfect for tabular data stored in CSV or Excel files. It gives you full control over split ratios and randomization. The image data generator method in Keras is designed for image datasets, organized in folders. It automatically handles both image loading and splitting with just a single line by setting the validation split. Finally, TensorFlow datasets, or TF.data pipelines, are ideal for large or streaming datasets. They let you split data directly in memory using the take and skip methods, which makes them very efficient for complex pipelines or GPU training. In short, pick scikit-learn for structured data, image data generator for folders of images, and tf.data for high-performance deep learning workflows. Chapter 4. Building Common Neural Network Architectures. Feed-forward neural networks, FNN. Feed-forward neural networks, often called FNNs, are the simplest and most common type of neural network. Data moves in only one direction, from input to output, with no feedback or memory connections. Each layer is made up of dense units, where every neuron is connected to all neurons in the next layer. These networks are great for tabular data, numeric features, or any structured dataset where each input is independent. We use activation functions like ReLU, sigmoid, or softmax to let the model learn complex relationships. Although simple, FNNs remain the foundation of deep learning, and mastering them prepares you for more advanced architectures such as CNNs and RNNs. Let's see how we build a simple FNN in practice. We start by loading the iris dataset using scikit-learn. It's a small classification dataset with 4 numeric features and 3 flower types. Next, we split the data into training and testing sets and normalize the features using standard scalar. This ensures all features have similar scales, which helps the network train more efficiently. Then, we create a sequential model with 3 layers: an input layer that matches the number of features, a dense layer with 16 neurons and ReLU activation, and an output layer with 3 neurons using softmax for classification. After compiling the model with the Atom optimizer and a categorical cross-entropy loss, we train it for 30 epochs with a batch size of 8. Finally, we evaluate the model on the test data and print the accuracy. In this example, the model reaches around 93% accuracy, a strong result for such a simple architecture. Convolutional neural networks, CNN. Convolutional neural networks are the backbone of most computer vision systems today. They are specifically designed to handle image data, where spatial patterns like edges, textures, and shapes are important. A CNN learns to detect features automatically using convolution layers. These layers slide small filters, or kernels, across the image and capture local patterns. Then, pooling layers reduce the size of the data while keeping the most important information. This makes the model faster and less prone to overfitting. After several convolution and pooling steps, the image is flattened and passed to dense layers for classification. The ReLU activation introduces nonlinearity, while softmax converts outputs into class probabilities. CNNs are used everywhere, from recognizing handwritten digits to detecting tumors or powering self-driving cars. Let's build a simple CNN using the M-NIST dataset. First, we load and reshape the image data into 4 dimensions: height, width, and color channels. Since these are grayscale images, we use one channel only. Then we normalize pixel values by dividing by 255. Next, we define our sequential model. The first conv2D layer uses 32 filters with a 3x3 kernel and ReLU activation. This is followed by a max pooling layer to reduce the image size. Then, we add another pair of convolution and pooling layers to extract deeper features. After flattening the output, we connect it to a dense layer with 64 neurons and ReLU activation. And finally, an output layer with 10 neurons using softmax for classification. We compile the model with the Atom optimizer and a sparse categorical cross-entropy loss. After training for 3 epochs, the network reaches around 99% accuracy, showing how powerful even a small CNN can be for image recognition tasks. Recurrent neural networks. Recurrent neural networks, or RNNs, are designed for sequence-based data. Data where the order of inputs matters, such as time, text, or sound. Unlike feed-forward networks, an RNN keeps a hidden memory state between steps. That means the output at any moment depends not only on the current input, but also on what it has already seen. There are 3 main types: simple RNN, which remembers a few steps but struggles with long sequences; LSTM, or long short-term memory, which includes special gates to manage long-term dependencies; and GRU, or gated recurrent unit, which simplifies the LSTM design but still performs well. These models are widely used in applications like text generation, speech recognition, and stock prediction, anywhere context and sequence play an important role. Let's now walk through how this simple LSTM model works, step by step. Our goal is to build a network that can predict the next word in a short sentence. We start by defining a very small text corpus. Deep learning with Keras is fun and powerful. Each word in this sentence will become part of a sequence we want the model to learn. Next, we split the text into individual words using the split function. Then, we create input-output pairs. The input is one word, and the target is the word that comes immediately after it. For example, input deep has target learning, input learning has target with, and so on. This teaches the model how one word follows another in sequence. After we build the list of input and target words, we need to convert them into numeric form because neural networks work with numbers, not text. We use the Keras tokenizer to assign a unique integer to each word in the vocabulary. For instance, deep might become 1, learning might become 2, and Keras might become 3. Once the words are encoded, we reshape the input into a 3-dimensional array. That means one sample, one time step, and one feature. This shape is required for all recurrent layers in Keras, including LSTM and GRU. Now we build the model itself. We use the Sequential API because our architecture is straightforward. The first layer is an LSTM layer with 32 memory units. This layer reads one word at a time and keeps a hidden state that carries information forward through time. After that, we add a dense layer with softmax activation. This output layer predicts which word is most likely to come next among all the words in our vocabulary. Then, we compile the model using the Atom optimizer and the sparse categorical cross-entropy loss function. Atom automatically adjusts the learning rate during training, and the loss function measures how far the predicted word is from the actual one. We train the model for 300 epochs, enough for it to memorize the word transitions in our tiny example dataset. Because the dataset is so small, training is almost instantaneous. Once training finishes, we test it. We give the model a single input word, in this case, Keras. We convert this word into its numeric form using the same tokenizer, reshape it into the right 3-dimensional shape, and then ask the model to predict the next word. The model returns a probability distribution across all words. We find the word with the highest probability, the predicted next word. Finally, we map that predicted index back to the original word using the tokenizer's word index. When you run this code, the model predicts is as the next word after Keras. That makes sense based on the original sentence. Even though this is a very small example, it demonstrates one of the most powerful abilities of recurrent neural networks: to learn context and relationships between elements over time. This same principle scales up to large models used in language translation, speech recognition, and even text generation systems like chatbots. Transfer learning. Transfer learning is one of the most powerful shortcuts in deep learning. Instead of training a model from scratch, which can take days or even weeks, you can reuse a pre-trained model that already knows useful patterns from massive datasets such as ImageNet. These pre-trained models, like VGG, ResNet, Inception, or MobileNet, have already learned to detect shapes, textures, and general image structures. We simply take these learned features and transfer them to a new task, for example, detecting car parts, plants, or medical conditions. The process is simple. Step 1. Load a pre-trained model with its existing weights. Step 2. Freeze most of the base layers so that their weights don't change during training. Step 3. Add your own custom layers on top that fit your specific task. Finally, train only these new layers first, and later, fine-tune the deeper layers if you need extra accuracy. Transfer learning saves enormous amounts of time and computing power, and it's one of the most common techniques used in real-world AI jobs, especially when working with limited data. Let's now apply transfer learning in practice using MobileNet version 2, a fast and efficient model that was originally trained on the ImageNet dataset. First, we load our own dataset using the image dataset from Directory Utility in Keras. We prepare both training and validation folders and resize all images to 160 by 160 pixels. Next, we load the MobileNet version 2 model, but we exclude the top classification layers by setting include_top to false. This keeps the convolutional base, which already knows how to recognize useful image patterns. Then, we freeze the base model by setting trainable to false. That means the pre-trained weights will not be updated during the first training phase. We now stack our custom layers on top, a global average pooling layer to reduce features, and a single dense output layer with a sigmoid activation for binary classification. After compiling the model with the atom optimizer and binary cross-entropy loss, we train it for just a few epochs. Even with very little training, this model can achieve over 90% accuracy because it's building on top of features already learned from millions of images. This is the essence of transfer learning. You borrow knowledge from a model trained on a large dataset and adapt it quickly to your smaller, task-specific dataset. Fine-tuning and freezing layers. Fine-tuning is the second stage of transfer learning. After you've trained your new top layers on top of a frozen base model, you can unfreeze some of the deeper layers and train them again, but this time, very carefully, using a small learning rate. Let's break down the two main ideas. First, freezing layers means locking their weights so they don't change during training. This keeps the pre-trained features, such as edge and shape detectors, safe. Second, unfreezing layers means unlocking them, allowing backpropagation to slightly adjust their weights. This helps the model adapt high-level representations to your specific dataset. For example, tuning from general animals to specific dog breeds or car parts. Fine-tuning can squeeze out that last 5 to 10% of accuracy. But if you unfreeze too many layers or train too long, you risk overfitting or forgetting what the model already knew. So always start with a small learning rate and unfreeze only the top few layers close to the output side of the network. Let's see how fine-tuning and freezing layers work in practice. We start by loading our dataset from folders and resizing the images. Next, we load the pre-trained MobileNet version 2 model without its top layers and freeze the entire base model so that none of its weights are trainable. We then add our custom layers, a global average pooling layer and a dense output layer with a sigmoid activation. We compile the model using the atom optimizer and binary cross-entropy loss and train only the new layers for a few epochs. After the top layers are trained, we begin the fine-tuning stage. We unfreeze the base model, but we keep most layers frozen. Only the last 40 layers are now trainable. These are the high-level layers that capture more specific image features. Next, we recompile the model with a very small learning rate, 1e to the power of -5, to make sure we don't destroy pre-trained weights. Finally, we train for a few more epochs. This small additional training phase fine-tunes the model and usually gives a few extra points of validation accuracy without overfitting or losing the generalization ability of the base model. This two-step process, training new layers first, then fine-tuning, is the most common and reliable workflow for real-world transfer learning projects.
Thanks for watching.